Hi, it's Guillermo. Today we are going to talk about one of the most famous algorithms in quantum computer, the Grover algorithm, that its main goal is to find a specific element in one unstructured dataset. This algorithm is well known for being able to achieve a quadratic speedup over the best classical algorithm. But let's stop here a bit and understand exactly what are these search problems and what means this quadratic speedup. So imagine that you want to try to guess what is my favorite number. And the only information that I'm going to give you is that it's an integer between 1 and 100. So a possible strategy that you can follow is ask me for possible solutions. Hey, is the number 2? And I will say no. Okay, is the number 10? No. And is the number 23? Okay, is the number 23? Perfect. So in that case, we will need 3 questions. But if we have 100 numbers, in average, we will need 100 divided 2. It means 50. What Grover say is that using these quantum ideas, only asking a squared of n, a squared of 100, it means 10 questions, we will be able to know what is my favorite number. And this is the important point. The quadratic speedup is in the average amount of questions that we have to do in order to find our element. In this video, instead of focusing how the Grover algorithm works, we are going to pay more attention in how we can use Grover for real applications. However, this first part is really important, so we are going to do a quick overview of the main steps of the algorithm. We can identify 3 main steps. First of all, we are going to create an equal superposition of all the possible elements in which we are looking for. For example, in the previous case, it will be an equal superposition of all the elements 1, 2, 3, 4 until 100, because that are all the possible numbers in which my favorite number is. The second step is apply the oracle. But what does it mean? Well, actually, there is a big misconception about this concept, so let's talk about that. The oracle is the function, the operator, the person that knows what is the solution. So, in the previous example, it was me. But then, if we have this operator that knows the solution, why don't ask directly, hey, tell me your favorite number? Why I have to do this game of try different options? It will be faster if we do it another way. It is not easy as that. The oracle doesn't know how to create a solution. We can't ask what is the solution because the oracle has no idea. The oracle only is able to identify if something is a solution or not. And well, let's put a very easy example to understand that. Personally, I'm really bad doing sudokus. So if you give me one, probably I'll not be able to find never a solution. However, if you give me one Sudoku complete, for me it's super easy to identify if it is correct or not. Because, well, I have to check the rows, the columns, that are all the numbers, whatever. But I'm able to do it. And this is the task that an oracle do. Check if a specific Sudoku complete is correct or not. A specific element is the element that we are looking for or not. So with this idea in mind, let's see how we can represent it in a quantum circuit. Actually, this oracle, this operator, let's call it O, what it's going to do is flip the sign of the elements that it considers a solution. For example, in our number election, if we have number 5 and we apply the oracle, the output is going to be 5, because this was not a solution. However, if we apply the oracle to the number 23, the output of the circuit now is going to be minus 23. It means we flip the sign of these elements that we consider a solution. And the third step is apply the amplifier or the Grover operator that is built in such a way that is able to take the negative elements and amplify the probability to watch them and reduce the probability of the elements that has a positive value. And let's put now everything together. Step number 1. We create this equal superposition of all the elements. Step number 2. We apply the oracle. In that case, we are going to flip the sign of the elements that we are looking for. and we are going to represent these states in red. Step 3, we are going to amplify these elements with the Grover operator, so the final solution will be something like that. But this is something that we can repeat and repeat to increase this probability. So now we can apply again the oracle. Now the element is going to be red again, and later apply the amplifier. So the chance of this element is increase and increase. There is a really cool geometric interpretation of this algorithm, but let's leave it for another moment, because now we are going to start to see how to apply this algorithm to real practical examples. Let's work with the inheritance problem. Let's guess we have a set of different properties, each of one with a different value, that we want to divide between two siblings. But we only want to find a combination that is a completely fair distribution. In this scenario, it's hard to create a solution, but actually it's super easy to check if something is correct or not. So we have all the ingredients to start to code the whole idea. Let's go to the notebook. Okay, so here we have a little summary of what is going to be our problem, the inherited problem. We have here the property prices for 8, 6, 3, 12, and 15. We have 6 variables because we have 6 properties, and in that case, if the variable xi equal to 0, means the property is for the first sibling equal to 1 for the second sibling. And the steps that we were going to follow were, first of all, we create the equal superposition of all the possible configurations, we apply the oracle to mark the elements that satisfy our conditions, and finally, we amplify the probability of the solution states through the Grover operator. So the first thing that we have to do is import our libraries, PennyLane SQML, and NumPy from PennyLane. After that, we are going to have two lists. The first one are the property prices, the one that we define in our problem, and then the list of wires that we are going to use. And we say we have 6 variables, we are going to codify each of these variables in 1 qubit, so we are going to need 6 qubits. So that's the main statement of the problem. The next step is define the oracle, this operator that is going to flip the sign of the elements that satisfy our condition. So in order to do that, we're just going to apply basic arithmetics, and the final circuit will be something like this one that we can see in the screen. The idea is very easy. If xi, in that case x1, is equal to 1, we are going to add to a counter, we are going to use auxiliary qubit for that. In this counter, we are going to add 4, because 4 is the value of the first property. And next, we will do the same for x2. If the value in x2 is equal to 1, let's add 8 to our counter. So after that, if we do that with all the properties, in the final registers, we are going to have the amount of value that the second sibling have. So what we'll do is check if this is, in that case, 24. It means the amount of all the properties divide 2. And if this is correct, we flip the element. At the beginning, that could sound a bit complicated, and you can see this function here. And for this reason, we have prepared a demo to learn all this main topic about basic arithmetic with the quantum Fourier transform. You will find the link in the description of this video. And with all of that, now we can define our circuit. So to do that, let's create our device. Device equal uml.device, and let's use the default qubit. In that case, the wires that we are going to use is, on one hand, these variable wires, the one that are codifying our variables, plus the auxiliary wires that we need to run the oracle. These wires that I'm going to save this counter of the amount of value of the properties of the second sibling. So after that, let's create our circuit. And let's go step by step. First of all, we have to create the equal superposition of all the possible configuration. So what we have to do, or let's say for wire in variable wires, let's apply a Hadamard. We only want the superposition in the variable qubits because they are the one that we want to try all the possible configurations. So after that, we have to apply the second step, that is use the oracle to mark these elements that are correct solution. So we just call the oracle function. In particular, we need to pass the wires of the oracle, and in that case are going to be the variable ones and the auxiliary ones. And finally, we need to apply the Grover operator. That is something that we already have in PennyLane. So we just call to the Grover operator gate. So we pass the wires. We want to amplify the values that are only in these variable wires. And then we can return the props of each of the basic state. So now, in order to see the solution, let's import matplotlib. Let's get the values of the different probabilities of each state, calling the circuit, and then we can plot it, something like plt.bar. So if I do that, we can see that there are two solutions that we amplify, and the other ones the probability decrease. But something that we can do to improve the probability of see these good solutions, because now is almost 14%, is repeat the second and the third step. In our case, what we can do now is for in range 3, we are going to repeat 3 times this process. Let's apply the oracle and then the Grover amplifier. We get now these states that basically now the chance of see one of the true values of these perfect configurations are 45% each of one. But well, we have here some integers that they are not actually the solution that we are expecting. So we have to get one sample to see what is actually the solution. In order to do that, we just going to ask for one shot. So we here shots equal 1, and instead of return the props, the probabilities, we are going to get a sample. So now, if I call the circuit, I get this solution 1 1 0 0 1 0. It means the second sibling is going to get the first, the second, and the fifth property. So let's check it. We can go to these values. 4 plus 8 is 12, plus 12, 24. On the other hand, 6 plus 3 is 9, plus 15 is 24. So thanks to this algorithm, we just found this perfect distribution. Actually, if you are wondering what is this other solution, it's just the symmetry. It means we are going to give to the first sibling the ones and to the second the zeros, but it will be that. We just see in this example that this algorithm works, but now maybe it's the moment to talk about the disadvantages or the limitations of this algorithm. That there are two main problems. First of all, sometimes a quadratic speedup is not good enough. In some scenarios, we work with a huge dataset. So this quadratic speedup over the linear one doesn't allow us to solve all the problems. And in second place is the first step of the process, and is the creation of the equal superposition of the elements that we are interested in. In our example, we just apply some Hadamards because, well, that was an easy example. But sometimes we are given a specific dataset, very concrete, was very unique elements, that the fact of creating this superposition is going to be a hard problem. So we have to find the equilibrium and know when we are going to need to use Grover. So I hope that in these few minutes you just learn a bit more about the Grover algorithm, what actually an oracle is, and how we can use it in different real applications. If you want to continue learning about this topic, I recommend you to go to the Xanadu codebook that I'm going to leave the link just in the description, and subscribe to the channel. Thanks to be there, and I'll see you in the next video.